The laws of logarithms are algebraic rules in which the logarithms behave. They tell us how, say we had a sum of two different logarithms, or the difference or a product of a logarithm with a constant number, how we could simplify those sorts of expressions. And these are really very similar to the laws of exponents. Like, say, for example, you have x squared multiplied by x cubed. We have a rule that says that if I have an exponential expression with the same base, and we're multiplying those together, we add the exponents together, and so on. Those are all based in common sense, and the laws of logarithms are very much the same, and the rules for how logarithms operate, if you actually pay attention closely, are actually the inverse rules to those laws of exponents. But one of the ways we can justify the laws of logarithms, which often I just refer to them as log laws, because it's shorter, but is by proving them using an exponential transition from logarithms to exponentials. Because reverting back to the original definition of the logarithmic function, a logarithmic function is always correlated to this an exponential equation, where if I have log base a of x and that's equal to y, that's always equivalent to a raised to the y is equal to x. Or, again, the basic idea of what does a logarithm do is it determines, well, a raised to what power will give me x? And the answer to that is y, which is why it's always synonymous to such an equation. That's how logarithms are defined, and that's why they work the way they do. And again, reasoning is to be an inverse to an exponential equation or function, and as we were talking about in class, we use logs to solve exponential equations, and vice versa, because it is its inverse. Reverting back to the laws of logarithms, because that's the key thing I wanted to mention today, let's first take a look at them, and then I wanted to prove to you why these are true. So the first log law says that if I have the log base a of capital AB, where those are multiplied together, then that's always going to be equal to the log base a of capital A plus the log base a of capital B. And in all of these log laws, what I recommend is that in each case, the base a of the logarithms could be anything. The lowercase a, just think of it as, well, these log laws work for any base. And as long as the base is consistent, what it's saying is if I add up two logarithms, that's always equivalent to the product of those two inputs to the logarithms multiplied together. And that can seem a little bit strange, but we can kind of view that as a sum turns into product. And almost in the exact same way, if I was to take a logarithm of a minus the logarithm of capital B, that would be equal to the logarithm of the ratio between a, b. So it's sort of like two logs combine into one, and then those inputs are combined. Addition changes to multiplication on the inside. Also, one way I like to say it is that because it wouldn't make sense for addition just to suddenly become multiplication. That's obviously different operations. But when I have the sum of two different, like addition on the outside of a logarithm, it changes into multiplication on the inside. Subtraction on the outside turns into division on the inside. And the last log law says that if I have c multiplied out front of a logarithm of a, where c is just like, kind of like if you have 3x, c would be like a coefficient. Say we had 3 times log a. What will happen is that will be equal to log of a raised to the c power. Or if you look at it in either way, because again, it's just an identity, it's an algebraic identity, meaning that these could be thought of in two different ways. You could also view, if you have a logarithm of an exponential expression, the coefficient, or the exponent, I mean, could drop out in front. And I remember, I remember one of my teachers drawing it like this, where I can take that exponent, just sort of drop it down, and that's always equal to c multiplied by the log of a. Kind of a strange rule, but basically these are algebraic ways to manipulate with the logarithms. And in the next video, I wanted to talk about how we can use these things. And what the last law, which is not usually referred to as a log law, but I often call it log law number 4, or it's usually called the change of base formula, states that if I have a log base b of x, where b is representative of a base different than a, then that's equal to the logarithm base a of x divided by the logarithm base a of b. Where again, a in each of these rules could be any base, and now we're talking about if we have a specifically based logarithm base b, what sort of this is saying is I could change that into a ratio of log of the input divided by log of the base, and that will always be equivalent as well. And again, I wanted to like talk about the proofs of these because the question is, well, why do logs behave in such a way? It's a little bit strange. And then in the next video, we'll practice using them and kind of seeing, well, what's the point? Why do we care about these? Why are these useful to us? But let's look at the proofs of the first three to begin with. And to prove these, it can be helpful to start off with the assumption that we're going to let a be equal to a to the x, little a to the x, and b be equal to little a to the y. And so this is kind of if you're not familiar with these sorts of algebraic proofs, it might be kind of strange to say, well, why am I doing this? What is the logic behind this? But my goal is to prove that if I'm trying to verify or understand those log laws for 1, 2, and 3, the first one states that log of capital AB is somehow equal to log A plus log B. And so what can be helpful, because A and B are representative of any numbers we want, anything we want them to be, really. But one thing about any number is it can always be expressed using an exponential expression. So let's just say capital A was 4. That would be equal to some base to the x power. And it's just sort of a way of saying, well, we're not really sure what this is, but the reason we're choosing base A is because the logarithm is base A, and it will be easier to see why these properties hold if we do this. And then, in the case of any base, there's always any exponent that will produce 4 due to the range of exponential functions, right? The range of exponential functions are 0 to infinity, meaning that assuming that these numbers are positive, I can find any exponential function that will work in such a way. And so that's I think that's the most difficult part of the whole problem conceptually, is why am I doing this? But you'll just see why this helps as we progress through the proof. And same thing for B. Basically, I'm going to take each of these components and let them be equal to some exponential function where basically x is going to be the exponent that would get me capital A, and y would be the exponent that would give me capital B. And given that assumption, since these are exponential equations, we can always translate an exponential equation to its logarithmic form by the definition of the log, right? Because if I swap x and a, that would leave me with log base a of a and equal x. And in the same way, if I swap y and b, because again, exponentials and logs are inverses of one another, so sorry, I was trying to draw with my mouse, but it wasn't working. But this equation is equivalent to this one by the definition of the logarithm, and this one as well. Since if I swap b and y, that would leave me with log base a of b is equal to y, because again, these are equivalent meanings. But anyways, why am I writing all this? This will help you see the algebraic steps that I'm going through. So to begin with, let's start with the left-hand side of log law number 1. And to review, those are on your packet. But they're also, in the slides right here, and somewhere in the textbook in 6.2 or 6.4, depending on which book you guys are using. But it's usually in the chapter on logarithms, or sometimes in textbooks it has its own section just on the laws or properties of logarithms. And anyways, so if we can start by making by substituting in this original assumption that A and B are just whatever numbers or algebraic expressions they want, but they could always be transitioned into an exponential form, which would leave us with a little a to the x and little a to the y, because that's what A and B were respectively. Well, why is that helpful? Because if I have exponential expressions to the same base, what will happen is it will change to a sum of the exponents, right? By rule of exponents, a to the x times a to the y results in a to the x plus y. It's like if you had a squared and a cubed, that would make a to the 5th. You would add those exponents together. And again, the reason why that's so helpful is because we have the combination of the product of those two things as a singular exponential expression now, and it has a common base of the logarithm. That was kind of the logic behind choosing those both base a. And of course, due to cancellation, log base a and a will cancel each other out, leaving us with simply x plus y. And as I said before, x would just be represented by log base a of a, because it's the exponent to which I would raise a to get to capital A. And for y, again, same deal there. Y is just equal to, well, what power do I take little a to get to b? Because again, that's exactly the purpose of x and y in those equations. And so that would leave me with simply x plus y, which are equal to, and so I could kind of think about substituting the second part into there, log base a of a plus log base a of b. And that is a algebraic proof of this. And for a lot of students, it can be a little bit difficult to grasp algebraic proofs, or it's easy to get a little bit lost in terms of what am I doing and why. In the next video, I want to show you guys some examples. I think it's a lot easier to understand how it works if we see it in action. But, I figured it would be important to show you guys the proof. And if that all makes sense, awesome. And we can definitely talk more about it in office hours if you have questions. Now, proof for number 2 is almost exactly the same. We're going to use the same exact substitutions. Let capital A be a to the x, and let capital B be little a to the y. If I substitute those in, that would leave me with a ratio of a to the x over a to the y, which again, if I have a division of exponential expressions with the same base, that always is subtractive, leaving me with a to the x minus y. And since, once again, I have a common base, a and a, log base a and a to the x plus x minus y, the logarithm base a will cancel the base a, leaving with simply x minus y. And as before, what is x? It is the exponent to which I take a to get capital A, which is represented by log base a of a, and y log base a of b. So once again, to summarize, if I have a product of two things within a logarithm, that's always equal to the sum of two separate logarithms of each of those factors. And if I have a ratio within a logarithm, same deal, it is equal to the difference between the logarithm of the numerator minus the logarithm of the denominator. And it really is a result of rules of exponential algebra. Now for the third log law, which has to do with an exponential expression within a logarithm. Now if I have log base little a of a to the c, these will not cancel because little a and capital A are not necessarily the same thing. But if I apply the same substitution, it's kind of like I'm changing this a into a base which is matching the logarithm. Again, that's the whole strategy here. Now I would have log base little a to the ax raised to the c. And now if I have an exponential expression little a to the x raised to the c, that would become a product a times cx, or a raised to the c times x, because stacked exponents always change into multipliers. Like if I have something squared and then I cube it, x squared parenthesis cubed, that would be x to the sixth. It's always a multiplicative effect when they're stacked like that. And in the same exact way, log base a and base a will cancel, leaving with simply cx. And as before, x was just equal to log base a of capital A, because x is the exponent to which I need to raise little a to get back to a. And that proves part number 3. And the last one, let's go ahead and prove the change of base formula as well, which is, just to reiterate, a way of taking a logarithm of any base and changing it to any other base that you want using a ratio. If we start on this side, this proof works a little bit differently. But if you start with the left-hand side here, log base b of x, and I just change that to y, that is helpful in progressing through the change of base formula. So what I'm going to start by doing is let y equal to the log of a specific base b. And the goal here is to change it to a base of anything, because that's the essence of how the change of base formula works. Now, if I set y is equal to log base b of x, I could always apply base b to both sides, or use the definition of the logarithm to change this to an exponential equation, right? Because this would be b to what power gives me x, and that I'm just letting be y. Then if I change the logarithm to its exponential form by definition, next what I could do is take the log base a of both sides. Now, we talked a lot about solving exponential equations already, and what I taught you guys to do is if you have a base b, apply logarithm base b, because it will cancel it out. But for this proof, it's helpful to not use the same base because we're trying to change the base in the change of base formula. So we're just going to let a be log base of anything, just not the same as b. But it could be, but we're just assuming it could be whatever we want. Obviously could be different from b. And then what happens next? So basically by log number 3, the one we just proved a minute ago, we could then drop the y out front because log base a to the b raised to the y is equal to y multiplied by log base a of b. So again, kind of how I like to think about it is that y could drop down, that's log law number 3, that always will be equivalent. And why does that help? Well, now I could solve for y, because originally that's what log base b of x is what I started with on the left-hand side of the change of base formula. And if I divide through by log base a of b, what we get is y is equal to log ax divided by log ab, and that is exactly the change of base formula. And again, because y is log base b of x. So just by using log number 3, we can see why the change of base formula makes sense. And that will wrap up this video. Next video, we're going to look at some examples. We're going to put into action. I'll show you how you use these and what's the sense behind their usefulness.